this video, we take a look at the dynamics of a simple pendulum. This video is specific to physics AB. So for example, this right here is a simple pendulum and it's obviously undergoing an oscillation. We've already looked at the simple pendulum in the context of conservation of energy, but what I never went through in that unit was a description of how F equals ma gives us this motion, nor did I go through the kinematics of this situation. That's what we're going to take a look at here in this video. Okay, let me go ahead and tilt my phone back towards the board. Like so. We'll tilt it upwards as well. Okay. Okay, so now we take a look at what is called the simple pendulum. And what we're going to do is apply F equals ma to the simple pendulum and then show in fact that it is a simple harmonic oscillator. Now notice what I've placed on the board here. Right over here is the differential equation, even though we didn't look at the calculus as such. This is the differential equation for a mass attached to a spring. For a mass attached to the spring, you have constants multiplied by position. This then equals acceleration. The square root of the constants that appears here in front of the position is equal to the angular frequency of the oscillation. What I'm going to do by analogy is apply F equals ma to the simple pendulum and show through a couple of steps that you obtain the exact same form of differential equation. That is, constants multiplied position equals acceleration. If you do, this then means that the pendulum is in fact a simple harmonic oscillator. The constants, however, that appear in front of the position will be different rather than the square root of k over m. We're going to see something else. Okay, I have it phrased for us as a problem. Go ahead and copy the problem down into your notes as I read it here. Show that omega is equal to the square root of g over L, where L is the length of the string for a simple pendulum. So we're going to show that the angular frequency of the oscillation is the square root of g over L. Here's how we go about doing so. Here's then how we apply F equals ma. Okay, so first of all, we have the pendulum itself of mass m and length L. Okay, right here is the vertical direction, and then let's say at the bottom of the swing here is the equilibrium position. Okay, and then by definition, like so, we have a displacement from the equilibrium position. We'll think of that then as x, and then right here is the angle that is made by the string with respect to the vertical direction. That's called theta. Okay, now there are just two forces exerted upon the pendulum, and that's tension and the force of gravity. So here's the tension vector like so, and here's mg. Now, unlike the conical pendulum, back in our unit covering uniform circular motion, I'm not going to resolve the tension T into components here. Instead, I'm going to resolve the mg into components. That is like so, and like so, where right here is the angle theta. Okay, now take a look at this component specifically of mg. Notice that this component here, mg sine theta, is in what is called the tangential direction. It's tangential to this circular arc. It is this component of mg that acts as a restoring force, much like, for example, the spring force. In this case, mg sine theta is trying to bring the pendulum back to its equilibrium position. So I'm just going to add up the forces in this tangential direction, where we would then result in what is called a tangential acceleration. I'm not going to worry about the resolution of the forces in this direction. In this direction, like so, towards the center of a circle, you do have a centripetal acceleration, but that's not important here for our purposes. We're only taking a look at the motion here along this circular arc, so I only have to worry about the mg sine theta. So let's go ahead and add up the forces in that direction. We get mg sine theta is equal to na, where the acceleration is what is called a tangential acceleration. This is a tangential acceleration. Okay, now let's go ahead and cancel out the mass m, like so. And then let's take a look at the equation as it is thus far. Notice that this expression here doesn't look anything at all like this expression here, where we have constants multiplied by position is equal to acceleration. So in order to make this expression look like that, I have to do a couple of extra steps. This is where we once again make what is called the small angle approximation. Recall the small angle approximation. The first time that you saw it was back in our unit on uniform circular motion covering the conical pendulum. So let me do a little bit of erasing here. Okay, let's recall the following. So recall the small angle approximation. In the small angle approximation, the sine of the angle, the tangent of the angle, and the angle itself are about the same thing as long as the angle is small. I did an example in one of my prior lectures where we chose a small angle, specifically 15 degrees. I converted that angle into radians, and then in radian mode on my calculator, I calculated sine and tangent of that angle, and we saw that all three of these numbers were about the same value. That's what's called the small angle approximation. Here's how I'm going to use it. What I'm going to do is I'm going to take the sine of theta here in the expression and just set it equal to the angle theta. Like so. And now to make this expression here look like this expression, I have to do one more step. And it has to do with the angle that is made by the string with respect to the vertical direction. Recall that angle is equal to arc length divided by radius, where this right here is the arc length of a circle. Recall that the oscillation takes place along a circular arc, and the radius of that circle, like so, is the length of the pendulum L. So let's go ahead and replace the angle theta here with x over L. That then gives us the following. This expression here. Compare this expression to this expression, and notice that it looks the same mathematically. That is, constants multiplied by position is equal to acceleration. Therefore, a simple pendulum, by analogy, is a simple harmonic oscillator. The only difference, of course, between this oscillation and earlier, the mass attached to the spring, is the angular frequency. The angular frequency, of course, is not the square root of k over m here. In this case, it's instead the square root of g over L. So even though we're not doing the calculus, of course, in this algebra-based class, what I have shown using F equals ma is that you end up with the same sort of differential equation as we already know for that of a mass attached to a spring. So then therefore a simple pendulum is a simple harmonic oscillator. The angular frequency of the oscillation is the square root of g over L. Okay, now let me demonstrate this expression for you, and we've seen it before. I'm going to write the expression in terms of period. So let me do this on the lower board. Okay, the period is 2 pi divided by omega. So then therefore, if you plug in this new value of omega, you end up with this expression here. Before I demonstrate it, by the way, notice what the period does not depend upon. It does not depend upon the amplitude. So then therefore, you can use a pendulum, for example, as a timing element in a clock. And in fact, the first mechanical clocks that were built after this discovery in the 17th century were in fact pendulum clocks. At any rate, however, let me go ahead and demonstrate the expression to you. I'm going to tilt my phone. So bear with me here as I do. Thank you. Okay, there we go. Okay, now first of all, let me set this into a small amplitude oscillation, so then therefore the amount of energy present is small, that is, like this. And then what I could do with a stopwatch, for example, is I can measure the period of the oscillation. Then let me go ahead and set it into a larger amplitude oscillation like so. When I do, there is more energy present, but the time necessary for one oscillation here is exactly the same as it was, for example, here when the amplitude was smaller. Once again, the period does not depend upon the amplitude, it only depends upon the length of the string L. Now, if I make the length of string smaller, say like so, notice how much shorter the period is here as opposed to here earlier when the pendulum length was longer. So if you make the length L longer and longer, the period then of the oscillation then, of course, increases. Actually, let me just continue to hold this by hand. Okay, now, as I said earlier, we've seen this expression for the period before. You specifically saw it in our unit on uniform circular motion when talking about the conical pendulum. Recall that the conical pendulum looks like this, where the object is in uniform circular motion, tracing out a circle that is parallel to the floor. The time necessary for one revolution to occur is exactly the same as the time necessary for one oscillation to occur. Recall that mathematically, there's really no difference between uniform circular motion and simple harmonic motion. It's just that in simple harmonic motion, you're looking at one component of the two-dimensional uniform circular motion, like so. In both cases, it's the exact same forces that are present, tension and gravity. So then therefore, because it's the exact same forces here as it is here, in both cases, that is, the period should be exactly the same, and it in fact is. Okay, now let me point my camera back towards the board. Okay, like so. Let me tilt it back up. Thank you. There we go, like so. Okay, let me do a little bit of erasing here. Okay, now let's go ahead and specifically describe the kinematics here of the simple harmonic motion for the simple pendulum. So because this is in fact a simple harmonic oscillator, this position equation, that is what describes the position as a function of time, is the same as it is for a mass attached to a spring. The only difference, of course, is that omega, the angular frequency of the oscillation, is the square root of g over L. Typically, however, with the simple pendulum, we usually don't bother describing x as a function of time. Instead, what we do is we describe the angle that is made by the string with respect to the vertical direction. This is what we usually describe as a function of time. So what I'm going to do is I'm going to replace the x and the a in this expression in the following manner. Displacement x is equal to angle multiplied by the length of string. So here on the left-hand side, let's write this as the length of string times the angle. And then on the right-hand side, we have the amplitude. The amplitude in terms of the angle is written in terms of what is called the amplitude angle. The amplitude angle is usually referred to as theta naught. So think of this as A, and then this right here will be the amplitude angle theta naught, and then multiplied by L. Like so, and then notice that the L cancels out. And so then therefore, the kinematics equation that we use to describe the angle that is made by the string with respect to the vertical direction is described as the following expression. Okay, let's go ahead and access an example that takes a look at the kinematics here of the simple pendulum. Let me move it here onto my screen. Okay, so we're going to do a couple of things here in this problem. Let me do some erasing first. Okay, and now we have the following. A simple pendulum has a length of 2 meters. So right off the bat, L is 2 meters. And the initial angle, the amplitude angle, is given to us as 15 degrees. So theta naught is equal to 15 degrees. Okay, in part A of the problem, we're going to find the angular frequency and then the period. So first of all, the angular frequency is the square root of g over L. Once again, this is the angular frequency of the oscillation. So I have the square root then of 9.8 divided by 2 meters. And this comes out to be about 2.21 radians per second. Okay, and then from there we'll find the period, which is 2 pi divided by omega. So 2 times pi and then divided by that. And this comes out to be 2.84 seconds. Okay, be a little bit careful later on when you review. These two numbers are pretty similar to each other, but this is the angular frequency of the oscillation, and this right here is the period of the oscillation. Okay, now in part B, it just says, write an equation for the angular position as a function of time. So we're just writing this equation here in part B. So the angle as a function of time is equal to the amplitude angle, and then multiplied by the cosine of omega t. Like so, where the value of omega is 2.21 radians per second. And now lastly in part C, let me move that here onto my file. Okay, part C, we're just taking a look at a specific point in the oscillation, or in this case, 2 points, and we want to calculate the time that the oscillation occurs at those points. So it says, when does the string make an angle of plus or minus 10 degrees with respect to the vertical direction? What we basically do is we assign one side of the equilibrium position as positive and the other side of the equilibrium position as negative. So if it says plus and minus 10 degrees, this means that we're going to calculate 4 total times. A time at positive 10, negative 10, negative 10, like so, for a total of 4 times with respect to one oscillation. So once again, we're looking at 2 different angles here, positive and negative 10 degrees. Okay, let me do some erasing here. Okay, here's our equation. Let me just leave it here. And now the easiest way to begin to visualize what's being asked for here in this problem is just to graph it out. So what I'm going to graph here is kind of like a kinematics graph, just like we did earlier in the unit. This is time in seconds. This is the angle in terms of degrees. And then we just trace out our cosine curve like so. Where here is 1 full period, so this is the time of 2.84 seconds from earlier. Let me make this a little bit straighter. There we go, like so. And then right here is the amplitude of 15 degrees on one side and negative 15 degrees on the other side. So let's take a look at positive 10 degrees first. So positive 10 degrees is right here, so we're going to find this time and this time. We'll be able to use symmetry to find the second time once we in fact find the first. So now let's go ahead and set the angle here equal to 10, like so. And then we'll do the remainder of the math here to solve for time t. So divide by 15 to the other side, take the inverse cosine of both sides. Like so. And now in which mode on my calculator do I have to be in? Do I have to be in degrees or radians? Radian mode. And the reason for that is because there's actually 2 angles here to worry about. One of the angles is the angle that you actually see, the angle that is made by the string with respect to the vertical direction. The other angle, if you will, is describing the angle in terms of the oscillation, the angular frequency multiplied by the time t. That's all in terms of radians. So you still have to be in radian mode here on your calculator in order to solve for the time. So let's go inverse cosine of 10 over 15, and then I'll divide by 2.21. And this then gives us our first time. This time, t1 is about 0.38 seconds. So for positive 10 degrees, pretty obviously that's this time right here. And then we could just use a little bit of symmetry to find the second time. I'll take 0.38 seconds and subtract it from 2.84. Okay, so 2.84 minus 0.38. Let's go ahead and do that math. So 2.84 minus 0.38, and this comes out to be 2.46 seconds. Okay, easy enough. Okay, and then let's take a look at the other side of the equilibrium position, so negative 10 degrees. So I'll find these 2 times, call them T3 and T4 respectively. So in order to find the first of those times, we'll take the angle and set it equal to negative 10 degrees like so. And then still in radian mode on my calculator, I then once again solve for the time t. So let me just do the whole thing for us here. Inverse cosine of negative 10 over 15, divide by 2.21, and I get that time, call it t3, to be 1.04 seconds. That's this point right here. And then by symmetry, t4 is 2.84 minus 1.04. That ends up being 1.8 seconds, like so. So an easy kinematics problem here. It's quite simple for the simple pendulum.